In this video, we're going to be discussing the topic of quantum mechanics. And we will be discussing what quantum mechanics means. Before beginning, we're going to complete a short review of the structure of the atom, and we're going to start with drawing the atom of magnesium. When we look at the periodic table, magnesium is atomic number 12. It's in column 2A and row number 3. Because magnesium is number 12 on the periodic table, we would draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 protons packed tightly together inside the nucleus where most of the mass is located. What we found out for atomic structure was that even though the inside of the nucleus, the inside part of the atom, the nucleus, is very important, really it's the outside part of the atom that's the most important. And the way we find out information about the outside of the atom is we have to go to the row number and we have to go to the column number. Because magnesium is in row 3, what we said is there are 3 energy levels. We call these 3 energy levels in which the electrons flew around within. So I've heard a couple of students call these rings. We're not calling these rings, we're calling them 3-dimensional spherical shapes. So we think of this sphere as a ping pong ball, and any electrons flying around in this sphere is like flying around on the surface of a ping pong ball, and maybe this is like the surface of a tennis ball. 3-dimensional areas of space in which the electrons are flying around. How do we know magnesium has 3 areas of space? Because it's in row 3. We call these areas of space energy levels. Then, when we go to magnesium and we find that it's in column 2A, the 2A refers to on the outside part of the atom, there are 2 what we call valence electrons or outer electrons, valence electrons, or bonding electrons. These are the most important part of the atom because this is the part of the atom that's going to connect, it's going to stick to, it's going to bond with other atoms, because as they fly around, that's the part of the atom that's going to hit each other. So there are 2 outer electrons, 2 bonding electrons, or 2 valence electrons. We have 3 different names for these. Then, if we go back to the periodic table, in order to find where all 12 electrons are located, remember, magnesium's number 12 because it has 12 protons and 12 electrons. We've already dealt with the 12 protons all packed tightly together in the nucleus, but the 12 electrons are arranged in these 3 energy levels. We already took care of 2 of them because those are the most important, so they identify it by a column number. Now we need to take care of the other 10. The way we take care of the other 10 is we walk through the periodic table. Very similarly to like playing a board game like Monopoly, and you roll the dice and you roll the 12, and now we're just going to walk through the periodic table. As we walk through, we count element 1, element 2. Both of those elements are in energy level number 1, so we put 2 electrons there. Then we get to energy level number 2, area of space number 2, and we count 1, 2, 3, 4, 5, 6, 7, 8. So now we put 1, 2, 3, 4, 5, 6, 7, 8. And then, of course, if we got to row 3, we would have counted over 2 spaces for magnesium. This is what we would call the atomic structure. The structure of the atom for magnesium. Now, it turns out that when we are dealing with the structure of the atom, it's not quite this simple. These 2 electrons, these 8 electrons, these 2 electrons are not always flying around in a nice spherical shape. It turns out that the shapes the electrons fly around in may be different than the shape of a sphere. So the question would be, well, why did we start with drawing them as spheres? This is a great tool. It's a great method to get to learn a simple idea of the structure of the atom before moving into what the atom actually looks like. And that is called quantum mechanics. The first thing that we're going to discuss within quantum mechanics is the electrons. Not all the electrons just simply fly around in a spherical shape. Right now, that's what we identified. If I asked you to talk about this electron, you'd say, oh, it's flying around in the shape of a ping pong ball very close to the nucleus. If I talked about this electron right here, you'd say, oh, it's flying around in the shape of a tennis ball, a spherical shape, a little bit further than the nucleus. So now what we're going to do is we're going to look at quantum mechanics. And the base of quantum mechanics is that there are 4 identifying factors for each electron. There are 4 identifying factors for each electron. Up here, there was really only one. It was just a spherical shape, and there it is. There are actually 4 identifying factors for each electron. So we're going to stop using. Now, I say stop using. I will probably accidentally keep using the term energy level, because these 4 do not have the term energy level. Some of them are similar to the energy level, and because I've used this term for the first several weeks of class, I'll accidentally refer to these as energy levels, but technically they're not energy levels. The first identifying factor for each electron is called the principal quantum number. Sometimes the principal quantum number is referred to as the shell. I will sometimes accidentally refer to it as the energy level, but technically it is called the shell. And you can have 7 different principal quantum numbers, and you will see why I accidentally referred to it as the energy level. Previously, we spoke about the energy level as being the row number. Row number 2, row number 3, row number 4. This is energy level 1, energy level 2, energy level 3, and 4, all the way up to energy level number 7. We found out during our last class, when we cut the periodic table up the way it actually should be, these last 2 rows fit into here, so there are only 7 rows on the periodic table. Some people say, well, why don't they just show it the way it is with these 2 rows up here and the periodic table split? I believe that it's just because it makes the periodic table very, very long, and it doesn't fit on a nice 8.5 by 11. So they take these 2 rows out and just make this fancy little description here showing that it fits up there. So here, now we're going to start referring. We're going to start referring to the row number 1 through 7 as the principal quantum number. This is found, so the principal quantum number is found by the row number on the periodic table. So it's found by the row number on the periodic table. And the information that it gives us, is the distance the electron is from the nucleus. And then I'll put on average, because the electron is flying around in a three-dimensional space. It's really an average distance the electron is from the nucleus. So if you have an electron in energy level number 4, it's going to be further from the nucleus than energy level number 3. So it's very similar. It has similar characteristics to what we've already talked about, where it gives us an idea of how far an electron is from the nucleus, just like when we were calling these energy levels. The second identifying factor for each electron is what is called the subshell. So we have the principal quantum number, or the shell. We also have what's called the subshell. And the subshell options are S, P, D, or F. 4 different subshells. This is going to be found by the area of space in which the element is located on the periodic table. So this is going to be found by the area of space in which the element is located on the periodic table, and the information that it gives us is the shape that the electron makes as it moves around the nucleus. Previously, we said that as the electron moves around the nucleus, it makes a spherical shape. So we said that the electrons were confined to an area of space that was a spherical shape, and we called it an energy level. Well, it turns out that not all electrons move around in a spherical shape. I wish they did, because it helps me think of the shape of an atom as a spherical shape. But not all electrons are going to fly around in a spherical shape. Some of them fly around in a different shape. So let's take a look at this a little bit more. So the first thing that I want to do is look at this, how we find it. We find the S, P, D, or F by the area of space in which the element is located. So in class, we drew out the extended periodic table, and this is a picture of what you cut and then colored for the extended periodic table. What I want you to notice is there are 4 different areas of space. There's an area of space identified as the S. There's a space identified as the P, a space identified as the D. The D is actually split, and then the area of space identified by F. And then, a couple of things. Very important, we moved helium from here over to this side. So when we were talking about metals and nonmetals, we actually said hydrogen belongs over on this side, but it's in column 1A because it has one valence electron. But we said it's a nonmetal, so it really belonged on this side, but we had to leave it in column 1A. And my favorite way to represent that is you separate it and put it up here, but most periodic tables just attach it here. So we just have to remember it is a non-metal. It belongs on this side with all the non-metals. Well, for quantum mechanics, we need to realize that helium actually belongs over on this side. So notice there are 4 areas of space: the S, the P, the D, and the F. Each one of these 4 areas of space is going to allow us to know the shape that the electron makes as it moves around the nucleus. So, for instance, if you are an element that has its last electron in the S subshell, that means this red piece here, that means the shape that your element is going to make as it flies around is a spherical shape. Here I've shown the 1s. So that would be energy level number 1 and S. So these 2 electrons here would be flying around in a spherical shape. Someone's going to say, well, wait a minute, Mr. Hodges, you just said earlier that they may not be flying around in spherical shapes. And that's true. Not all of them are, but if you are in an S subshell, notice there are 4 subshells, S, P, D, or F. If you're in an S subshell, you are electrons that are flying around in a spherical shape. Well, what's different from this first row, the 1s, versus the second row, the 2s, or the third row, the 3s? Well, very similar to our energy levels previously. It just means the subshell, the S area of space, the sphere is getting bigger. So, for instance, the electrons for hydrogen and helium in the 1s are flying around on the surface of this sphere. Then the electrons for lithium and beryllium are flying around in a surface of a sphere that's bigger. So you can picture this sphere being superimposed on top of this sphere. And if we were talking about beryllium that has 4 electrons, 2 of its electrons would be flying around on the surface of the 1s sphere, and 2 of the electrons, the sphere would be right on top, superimposed, 2 of its electrons would be flying around in the 2s sphere. Mr. Hodges, that's kind of what we originally did. Yes, but the shapes are going to be changing. If we were talking about lithium, we would say 2 of its electrons would be flying around in the 1s, so 2 electrons on this surface, and it only has 1 electron because it's the first one there in the 1s, in the 2s, and so this sphere would be superimposed on top of here, but there would only be 1 electron flying around. 2 on the inside, 1s, and 1 on the outside, the 2s, because it's the first one there. Well, what about the other shapes? What kind of shapes do P and D and F make? Well, the P orbitals, there's actually 3 shapes to the P orbitals. They are almost these like ice cream cone looking connected shapes. I want to remind you, I like this picture here because this would be someone taking a picture on their shutter mode or their super fast mode on their iPhone and taking pictures of the electrons as they're flying around in a p orbital. And this is what it would look like. So this is the shape the electrons make if they're flying around in a p orbital. Now, we'll get to why there are 3 different shapes. Here's the first shape. We call it a px. Here's the second shape. We call it a py. Here's the third shape. We call it a pz. So now, if we are in a p orbital, If we're in a p orbital, that means we're in this area right here. So if we go all the way back, we don't start with 1p. There are no 1s for the p. We start with 2p. And when we start with energy level 2, notice I accidentally said energy level instead of principal quantum number or shell. I told you I would do that. If we start with principal quantum number 2 and work our way across the periodic table, we start with 2 S's and then we go to 2 P's. And it turns out that there are 3 shapes of the P's as you move across, and these are the shapes. So the electrons are not always flying around in a spherical shape. They're also flying around in this weird lobe-looking shape. Well, what about the D's? What kind of shape if you're an electron in a d orbital? The d orbitals have 5 different shapes, and you can see that they get even more complex as we go. Here's the first, the second, the third, the fourth, and the fifth. And these pictures here are showing what if we took a picture on a super fast mode of an electron flying around, and it makes this 3-dimensional shape, or this one. They call them d sub yz, d sub xy. 5 different shapes. One of the things that I want to point out to you is you can only have 2 electrons per orbital. 2 electrons per orbital. So let's look at the S. As we move across the S, we count 1, 2. As we move across the S, 1, 2, 1, 2, 1, 2. There's always only 2 as we go across. Since there's only 2 electrons as we go across, we're only going to need 1 orbital. So when we look at the S's, the 1s going across only has 1 orbital. Why? Because there's only 2 electrons. The 2s, there's only 1 orbital. Why? Because there's only 2 electrons. If we had the 3s, it would just be a bigger sphere, and there would only be 1 orbital because there are only 2 electrons. But let's count the p's going across. When we count the p's going across, 1, 2, 3, 4, 5, 6. Well, if 2 electrons can fit into each orbital, and there are 6 electrons going across this p orbital, that means we're going to need 3 orbitals to fit all 6 of those electrons. So when we go and look at the p's, how many orbitals do we have? We have 3. 1, 2, 3. That's why the p has 3 orbitals, because each orbital can only fit 2 electrons. And when you count across the p's, you have 6 electrons, so you need 3 orbitals. But the s going across, you only count 2 electrons, so you only need 1 orbital for each row or principal quantum number. How about the d's? Well, let's count. We got 1 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 going across. 10 electrons going across as we fill up the d's. Well, if there's only 2 electrons per orbital, how many orbitals do we need? Well, it turns out that we need 5. And there are the 5. The 1, 2, 3, 4, 5. So 2 electrons can fit into this. 2 electrons, 2 electrons, 2 electrons, 2 electrons. 2 electrons can fit into each one of those areas of space, just like the p's. 2 electrons, 2 electrons, 2 electrons. Once the 2 electrons go in, it is full, and you cannot put any more electrons in. Same thing with the s. It can only fit 2. It can only fit 2. So the s, p, d, and f are found by the area of space. The element is located on the periodic table, and it gives us an idea of the shape that the electron makes as it moves around the nucleus. Now, there are 7 F's. I did not print out the different shapes, but we will find out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 going across, so there will be 7 orbitals for the F. The third piece of information, remember we're working through the 4 identifying factors for each electron. And the third one that we're going to talk about is called the orbital. And the orbital depends on which subshell the electron is located. As I mentioned, the S has only 1 orbital. The P has 3 orbitals, and we will label them as either the X, the Y, or the Z. The D has 5 orbitals. We will label those as 1, 2, 3, 4, 5. And then the F has 7 orbitals, and we will label those as 1 through 7. Now, technically, when we look at these, the p orbitals are labeled as px, py, pz, conveniently identified by the axis in which they are running along or located. The D, as abbreviations, we just call them 1 through 5, but really the first is the dyx because it's along the plane of the y and the z axis. So dyz, I think I accidentally said dyx, but it's dyz because it's along the yz plane. Dxy excuse me, is along the xy plane. Dxz is along the xz plane. Dx squared y squared is along the xy plane, but notice it's shifted. This is at an angle to this. And then the dx squared, I always think it's interesting, there's this donut shape in between these two. I don't know why electrons are flying around in that type of shape, but those electrons are designated toward that type of shape. So what we will say is the orbital is going to be found by the position of the element within the specific subshell. And the information that it gives us, is it allows us to know which orbital which specific orbital the electron is located. And in many cases, which axis the electron is located. Finally, we're going to be dealing with the electron spin. And the electron spin is designated either by an up arrow or down arrow. And we can think of these electrons just like the Earth is rotating around the sun, the Earth is also spinning. So as these electrons are flying around, they're also spinning on its axis. So we can either label it as a clockwise spin or a counterclockwise spin. But electrons have one type of spin or another type of spin. So it's either clockwise or it's counterclockwise. And what we find out is they must have opposite spins. If they're going to be in the same orbital, electrons in the same orbital must have opposite spins. And then finally, I'm going to come up here, and I apologize, I'm going to squeeze another piece of information in here. Each orbital must be half filled before any are complete. So I'm just going to add in the half filled rule, as you already have taken these notes on the back side of your extended periodic table. So we don't need to add that whole sentence again. Just as a note, there is a half-filled rule, meaning each orbital must be half-filled before any are complete. Now, for the S, it does not matter because there is only one orbital. So one electron goes in, the next electron goes in. One electron goes in, the next electron goes in. Just like I said, one electron, then the next. One electron, then the next. But it does matter when we get to the P's for the half filled, because there are 3 orbitals going across the P. But the rule states that each orbital must be half full. So when I put this first electron in to the px orbital and it's flying around, the next electron here does not go into that same orbital. It goes into the next one. And then the next electron, which would be for nitrogen's last electron, it would go right here. Then each orbital has 1 electron. Now we can go back and fill in. So when we get to oxygen, the next electron goes here, then the next one goes here, and the next one goes here for fluorine and neon. So boron, who gets its first electron in the P, its electron's flying around there. Then carbon, the next one, its electron flies around there. Then nitrogen, its electron flies around there. Oxygen, now each of them are half full. So oxygen, the next electron goes here. Then for fluorine, the next electron goes here. Then for neon, it goes here. And we'll talk about how that looks when we fill in the orbitals for the P. I hope this helps in getting an idea that quantum mechanics is dealing with 4 identifying factors for each electron. No longer are we thinking of the electrons as flying around in simple spheres. We are now thinking of them as having a principal quantum number, and that gives me information. A subshell, that gives me information. An orbital, that gives me information. And the electron spin, that gives me information.